Digital logic gates are electronic components that perform logical operations on binary inputs and produce a single binary output. They are the basic building blocks of digital systems like computers, calculators, and microcontrollers. This video explores the types, functions, and applications of digital logic gates, along with their implementation using different technologies. A digital logic gate is defined as an electronic circuit that makes logical decisions based on the digital signals at its inputs. A digital signal represents either a logic level 0, low, or 1, high. Typically, a logic 0 is 0 voltage or ground, and a logic 1 is a positive voltage, like +5 or +12 volts. A good example of a digital state is a simple light switch. The switch can be either on or off, one state or the other, but not both at the same time. Then we can summarize the relationship between these various. Most digital logic gates and digital logic systems use positive logic, in which a logic level 0, or low, is represented by a 0 voltage, 0 V, or ground, and a logic level 1, or high. Digital logic noise. Noise is the name given to a random and unwanted voltage that is induced into electronic circuits by external interference, such as from nearby switches, power supply fluctuations, or from wires and other conductors that pick up stray electromagnetic radiation. Then, in order for a logic gate not to be influenced by noise, it must have a certain amount of noise margin or noise immunity. The noise signal is superimposed onto the VCC supply voltage, and as long as it stays above the minimum level, VON, minute, the input and corresponding output of the logic gate are unaffected. But when the noise level becomes large enough and a noise spike causes the high voltage level to drop below this minimum level, the logic gate may interpret this spike as a low-level input and switch the output accordingly, producing a false output switching. Then, in order for the logic gate not to be affected by noise, it must be able to tolerate a certain amount of unwanted noise on its input without changing the state of its output. A digital logic gate can have one or more inputs, but generally only has one output. The output depends on the type of logic gate and the values of the inputs. The relationship between the inputs and the output of a logic gate is expressed by a truth table, which shows all possible combinations of input values and the corresponding output value. The digital logic gate is the basic building block from which all digital electronic circuits and microprocessor-based systems are constructed from. Basic digital logic gates perform logical operations of AND, OR, and not on binary numbers. There are 7 basic types of digital logic gates: NOT and OR, NAND, NOR, XOR, and XNOR. Simple basic digital logic gates. Simple digital logic gates can be made by combining transistors, diodes, and resistors, with a simple example of a diode resistor, DRL, and gate, and a diode transistor logic, DTL, NAND gate shown in Fig. The simple 2-input diode resistor and gate can be converted into a NAND gate by the addition of a single transistor inverting NOT stage. Using discrete components such as diodes, resistors, and transistors to make digital logic gate circuits are not used in practical commercially available logic ICs, as these circuits suffer from propagation delay or gate delay and also power loss due to the pull-up resistors. Another disadvantage of diode resistor logic is that there is no fan-out facility, which is the ability of a single output to drive many inputs of the next stages. Also, this type of design does not turn fully OFF, as a logic 0 produces an output voltage of 0.6 V, the diode voltage drop, so the TTL and CMOS circuit designs are used instead. Basic TTL logic gates. In standard TTL, transistor logic ICs, there is a predefined voltage range for the input and output voltage levels, which define exactly what is a logic 1 level and what is a logic 0 level. The simple diode resistor and gate uses separate diodes for its inputs, one for each input. As a bipolar transistor is effectively 2 diode junctions connected together, representing either an NPN, negative-positive-negative, device, or a PNP, positive-negative-positive, device, the input diodes of the diode transistor logic, DTL, circuit can be replaced by one single NPN transistor with multiple emitter inputs to form another type of logic circuit called transistor logic, or TTL, as shown. This simplified NAND gate circuit consists of an input transistor, TR1, which has 2 or more emitter terminals, and a single-stage inverting NPN switching transistor circuit of TR2. When either or both of the emitters of TR1 representing inputs A and B are connected to logic level 0, low, the base current of TR1 passes through its base emitter junction to ground, 0V. TR1 saturates and its collector terminal results in the base of TR2 becoming connected to ground, 0V. Hence TR2 is OFF and the output at Q is high. With both inputs A and B high at logic level 1, input transistor TR1 turns OFF. The base of switching transistor TR2 becomes high and turns it ON, so the output at Q is low due to the switching action of the transistor. The multiple emitters of TR1 are connected as inputs, thus producing a NAND gate function. Emitter-coupled digital logic gate. Emitter-coupled logic, or simply ECL, is another type of digital logic gate that uses bipolar transistor logic where the transistors are not operated in the saturation region, as they are with the standard TTL digital logic gate. Instead, the input and output circuits are push-pull connected transistors with the supply voltage negative with respect to ground. This has the effect of increasing the speed of operation of the emitter-coupled logic gates up to the gigahertz range compared with the standard TTL types. But noise has a greater effect in ECL logic, because the unsaturated transistors operate within their active region and amplify as well as switch signals. With improvements in the circuit design to take account of propagation delays, current consumption, fan-in and fan-out requirements, etc., this type of TTL bipolar transistor technology forms the basis of the prefixed 74 family of digital logic ICs. Basic CMOS digital logic gate. One of the main disadvantages with the TTL digital logic gate series is that the logic gates are based on bipolar transistor logic technology, and as transistors are current-operated devices, they consume large amounts of power from a fixed plus 5-volt power supply. Also, TTL bipolar transistor gates have a limited operating speed when switching from an off state to an on state and vice versa, called the gate, or propagation delay. To overcome these limitations, complementary MOS called CMOS, complementary metal oxide semiconductor, logic gates which use field effect transistors, or FETs, were developed. As these gates use both P-channel and N-channel MOSFETs as their input device, at quiescent conditions with no switching, the power consumption of CMOS gates is almost zero, 1 to 2 microamp, making them ideal for use in low-power battery circuits, and with switching speeds upwards of 100 MHz for use in high-frequency timing and computer circuits. This basic CMOS gate example contains 3 N-channel normally off enhancement MOSFETs, one for each input consisting of FET1 and FET2, and an additional switching MOSFET, FET3, which is biased permanently on through its gate. When one or both inputs A and B are grounded to logic level 0, the corresponding input MOSFET, FET1 or FET2, are switched off, producing a logic 1 high output condition from the source terminal of FET3. Only when both inputs A and B are held high at logic levels 1 does current flow through the corresponding MOSFET, switching it on, producing an output state at Q equivalent to a logic level 0 as both MOSFET, FET1 and FET2 are conducting, therefore producing the switching action representative of a NAND gate function. Improvements in the circuit design with regards to switching speed, low power consumption and improved propagation delays has resulted in the standard CMOS 4000 CD family of logic ICs being developed that complement the TTL range. Like TTL logic, complementary MOS, CMOS, circuits take advantage of the fact that both N-channel and P-channel devices can be fabricated together on the same substrate material to form various logic functions. One of the main disadvantages with the CMOS range of ICs compared to their equivalent TTL types is that they are easily damaged by static electricity. Also, unlike TTL logic gates that operate on single 5 volts voltages for both their input and output levels, CMOS digital logic gates operate on a single supply voltage of between 3 and 18 volts.